बैटरी का इशू है सर. So very good morning and welcome to day 4 for this GIAN course on combustion theory and applications. So till previous lectures we have emphasized the concepts of combustion modeling and how chemical kinetics concepts were brought into picture, how to frame the governing equations, what are the different combustion parameters that needs attention while modeling. Here I will start some basics of laminar premixed flame. In fact, my other colleagues, Professor Markus also, he will be talking similar concepts, but however their, although theories are same, but their his way of looking at the things may be different with research point of view, but as far as the course is concerned, we are going through the theory part. So in this lecture the main intention would be I will touch upon the first basic phenomena of combustions, which starts with formation of flame, its propagation. We will try to see, and first simple type of flame is laminar premixed flame. This is something similar to the fact that when you have spark ignition engines where fuel and air mixture is burned together, and it is the, we call this as a homogeneous mixture. When you ignite it through a spark plug, it creates a flame. Flame is nothing but a surface that essentially distinguishes the region between the charge and the combustion products, and in the combustion medium the flame propagates or moves. When it moves, because of the increase in the pressure and temperature of during combustion, it also subsequently moves to ignite the fresh charge. This is essentially required that we need to develop some kind of phenomena or mathematical models, concepts during the time of combustions. You can see this such type of events only last for few milliseconds, and that few milliseconds it initiates with a flame, subsequently burning all the fuels, and and letting the combustion products out, which means that we are looking at the domain of that test window in which flame is generated, it moves, and finally its main intention is to ignite all combustion products. Initial ignition was given manually into the charge, but subsequent ignition happens due to this flame motion. So, because of these reasons, because we need to have a sustained flame, the flame has to remain, flame has to be there in that domain till all the fuel air mixture burns completely. Then only we can have a effective meaning of combustions. But however, to have a sustained flame, we also expect that we should create some favorable conditions for that sustained flame. So, that is the reason we need to discuss about different factors that influences the flame velocity. And over the period of time, people have done lot of experiments, and among variety of parameters has been studied, and they are simplified by certain correlations, and we call them as a laminar flame pleats correlations, which more or less is agreeable to all kinds of combustion involving premixed charge. As a case study, I will try to see that how that concept is normally extended for homogeneous mixture combustion in a spark ignition engines. As far as these two parts is concerned, wherever we encounter IC engine cores, we normally start with homogeneous mixture combustions, and subsequently how that combustion effects gives rise to variety of phenomena, whether it is a unwanted combustions or it is a favorable combustions, and that is mainly because the kind of laminar flame that we can generate, and subsequently we need to evaluate that effect. If at all that laminar concepts was not favored, then what are the effects that we are going to see if the combustion is not complete. So, this is the overall things concepts about this lecture today. So, when you talk about modes of combustions, we normally think about two things. One is flame mode. In the flame mode, we have a spark plug, and through this spark plug the flame gets initiated, and in this zone all the phase charge gets burnt. Then subsequently the flame moves in the directions of unburnt fuel air mixture and slowly killing all this unburnt charge into combustion products. So, ideally, if this is the domain of domain that flame has to move and propagate, then which means that starting from initiation of the flame, it has to go, and by the time we initiate the flame and it reaches here, all the combustion products has to be burnt. This is how we do a flame mode combustions. In other things, where you talk about non-flame mode, either in the non-flame mode, normally instead of spark plug we use fuel injector, and this fuel injector, what it does is that there are possibilities that you can inject this fuel at various locations, and through this we can auto ignite this charge. The auto ignite charge means air and fuel come separately, and they are already in this when the fuel sees that high temperature pressure air, then it self ignites. Although there are flames, there are multiple number of flames that opens up simultaneously, but we cannot actually create a specific flame that ignites the fresh charge. So, that is actually we call this as a non-flame mode combustion. So, whatever may be the situations, in this laminar premixed case, we will mostly concentrate on a propagating flame which is initiated by a premixed charge. Many times in engine point of view, if the charges are not ignited completely, it creates an effect which is called as a knock. This knock is a undesirable situation that we encounter in the cylinder of an IC engine, and that is quantified in terms of rapid pressure rise, and it leads to undesirable sound of the engine. So, we will talk about these things, how this knock will form in subsequent slides. The kind of other mode of combustion that we call in this situation where we use this fuel injector, in which we have a non-flame mode situation. Such things we call them as a diffusion flame. It has, although it is not exactly diffusion, but we can say it is partially premixed or partially diffusion burning. Then we will move on to the physical features of laminar flame. As you must have seen in our previous lectures given by the Professor Markus, he talked about what is the initiation of the flame. It started with a flame. The flame would have a velocity, it has a certain velocity, and if it has to move in a particular directions, the propagation of charge and flame velocity should be same. That is the first criteria. Second thing, when the flame speed, when the flame moves, it is also moves with certain speed. It is followed by the charge which is moving behind it, and through this process, if and the charge which moves it is in such a way that the flame speed and your charge speed, they may or may not be different. So, what one particular situation, at least the minimum condition is that the flame velocity should be same as the charge which is moving behind it or unburned gases. In some cases, flame travels at subsonic speed, some cases it travels at supersonic speed. So, accordingly, that word laminar flame is termed as deflagration or detonation. Other kind of characteristics that is also required, the flame speed and thickness. This flame speed and thickness is controlled through this equivalence ratio, temperature and pressure, and of course the fuel type. And it also this flame speed detects the flame shape, stability, such as blow off or flashback. That means, as you told, if the flame has sufficient momentum, it can move towards the unburned gases and burn them. If it does not have, there are chances it can flow back. Such, and if it has a more momentum, the flame will be moved most faster. So that way two situations can land up, one is blow off or flashback. So those things we will try to discuss. The other concept that we also need to explore, the flammability limit, ignition and extinction. So flammability limit, normally in ICE engine we say the equivalence ratio falls in certain range for initiation of the flame, or otherwise flame cannot be initiated. So during this period we can see a self-sustained flame, and that is the reason it is quantified through the flammability limit of any charge. Then ignition. Ignition is the instantaneous phenomena that has to be there to create the to initiate the flame. Sometimes the flame has to be extinguished because it can create something effects, undesirable effects of explosion. So that thing will also require the concept of flame extinction. That means with that point of time we should somehow kill this flame speed to reduce its momentum. So all these parameters has to be looked into the discussion while talking about homogeneous combustion, and we need to understand them through these characteristics of temperature profile. So here what we look at, we define a term what is called as flame speed, which is SL. We need to view this flame speed, and by definition this flame is stationary relative to a laboratory frame in which the reactant enters the flame with a flame propagation velocity SL. So flame speed and flame propagation velocity of the reactants or charge has to be same. So this is how we get that relation through this continuity equation, that conditions which happens to be before unbound charge and after unbound charge. Now and this condition has to be satisfied for creating this flame. That means continuity equation that involves any arbitrary frontal area which involves density and the speed. Now coming back to its temperature profile, this is the generic trend, how the flame propagates in a medium. Like here the flame is moving from right to left by carrying certain energy with it, and with that energy it is trying to burn the unburnt fuel air charge. So if you look at this as a x, so we are looking at in this x axis we say it's axial distance, and we are trying to see how the changes that happens when the flame moves. So initially when there is no flame, it is the full of charge. When the flame happens, through this there are changes in the various factor. First temperature, mole fraction. Mole fraction means once the charge gets consumed, its mole fraction comes down. So basically reactants are consumed, products are formed, and through this process there is a volumetric heat release. So the trend of these things is defined in this manner, that the mole fraction of the reactants comes down with axial distance. At one point of time it is almost 0. At that location we see this maximum heat release, and this is the typical plot that we normally encounter when you do experiments of heat release diagram, something we call as a P theta diagram in the IC engine terminology. and through this initially the temperature is with respect to that of the condition which is at the reactant, slowly it increases maximum, and since this heat release diagram is impulsive in nature, so the temperature profile happens to be parabolic for corresponding to this impulsive nature of the heat release. So, this is standard characteristics. We can say the temperature, although because temperature is rising slowly because of this heat, and what is peak heat release and maximum temperature location may be seen at some different location. And when you talk about some other term like you can imagine this, for this thickness of this flame could be much lesser than 1 mm or maybe less, like and during this fast reaction we for a self sustained flame, and we require some driving force. So, driving force is nothing but the momentum the flame carries with it, and that comes from the heat that is released during the ignition process. If the heat is sufficient, then it drives the flame. If it is not sufficient, we cannot ensure a self sustained zone. You cannot ensure a self sustained flame. So, because of this reason, the entire temperature profiles is characterized by two zones. One is preheat zone, other is reaction zone. During the preheat zone, you will find the reactants concentration or mole fraction in a higher to be higher. When reaction once the reaction is done, the charges gets consumed, temperature shoots up. That time those things we call this as a reaction zone, and all the reactions during this phase only all reactions takes place through their element either it in the form of elementary reactions and also in the form of global reactions. So, the secondary zone extends to several millimeter means of atmospheric pressure, which means at this phase only your pressure rise is significant. Here another important aspect is that for hydrocarbon flames, the radicals CH that takes the dominance, and sometimes if depending on the conditions of stoichiometric, we get some kind of radiations either due to this carbon, and that is termed as blue green zone, and when OH radicals are formed, it gives to a reaction where carbon monoxide gives CO2. Now, in our previous lecture, we said that carbon always CO always needs to tend to mix oxygen to form CO2 if it gets a favorable environment, and through this formation it releases some radiation energy in the form of H nu, and this nu is basically talks about luminescence of the chemical luminescence of this reaction. Now, when the flame becomes richer, soot formation comes, so it becomes a continuous black body radiation. This is a typical feature of a Bunsen burner flame that highlights and in order to see all those effects, we need to bring this concept of Bunsen burner flame, where what sir was explaining before, that we have a regulated knob which controls the air entering into it and fuel entering into it, by controlling the knob, we can generate two types of flame, laminar or diffusion flame. So typically when you, for a Bunsen burner flame, it is characterized by two things. One is inner cone, other is outer cone. Inner cone is called as premixed flame and outer cone is diffusion flame. So this inner premixed flame is formed in the inner region with this, and that is mainly due to what air and fuel that enters with our control. But when this inner flame has a tendency, once it is framed, a tendency to mix with outside air. So that way when it mixes, it gets diffuses with outside air. So through this process we don't have any control of, there is no control of premixed concept. So it forms a outer cone, and that is called as diffusion flame. So this is the one characteristics that a Bunsen burner flame can give, where both premixed and diffusion flame. Now coming back to this inner flame cone, if you try to mathematically model this model the analysis, we can say we can have one angle. Since it is a inner cone, we can define an angle alpha, which is called as local angle. The film sheet meets with a vertical plane, and there we have two velocity. One is unburned gas velocity. This can be decomposed along one axis of the cone and perpendicular to it, and this is with respect to the length of this cone, and other is normal to it. So for flame to be in a remain stationary, the flame speed must be equal to the speed of normal component of the velocity. So this condition has to get satisfied. So now other features of some laminar flame which replicates the similar phenomena, they are also seen in radiant burners. So this is with respect to engine, but this is with respect to burner applications. So actually when you see this in this particular applications, when you use this combustion as a household applications of designing the burners, we have different mechanisms in which the burners can be made, and they are mostly governed specifically through laminar flame, because we normally regulate the air and fuel, where we have the charge and it takes the atmospheric air, and we see the flame on the top of the burner. That is what you see in conventional cooking stoves. So but there are variety of ways we can design these radiant burners that can be categorized in two parts. One is adiabatic burner, other is non-adiabatic flame burner. So this is something like those burners are designed to create flat flame. Here it is a planar flame, this is a flat flame. The design features involves boro structures, as we discussed yesterday. There may be some screens, glass balls, where fuel air mixture enters, and subsequently we generate the flame. Other structures is in this case we have similar to this glass ball, we have also the mechanism of improving the flame speed of the premixed charge, and the size of those holes essentially detects whether the charge will go in the forward directions or not, and these designs are very vital to ensure a sustained flame. So, what you see this flat flame on the surface, if it has to remain continuously as long as this fuel charge is there, it has to remain on the surface. These geometrical conditions as well as the fuel condition has to be ensured simultaneously. So, for laminar flame, the maintaining a sustained laminar flame is really challenge when you are looking at particularly for burner applications. I also mentioned that when the flame sits on the surface, that means always this charge, always the charge should have sufficient momentum, so that flame remains on the burner, and if it does not have, it tries to move down. So, always one condition is, that means there are two possibilities. The flame can sit on the surface, that is the most ideal case. The flame may blow up. Blow up means it has sufficient momentum, it does not sit on the surface, rather at some distance from this surface. Other situation could be the flame can propagate back. Propagate back means if that condition is not maintained, unbound charge gas and flame velocity, when it goes back, so it can directly come to this fuel air charge, that means flame is moving back. So, this kind of situation creates the explosion. So, we call this as a flashback. To ensure this flashback not to happen, we require some kind of mechanism in the form of flame arrestor, or this kind of design will help you whether we can arrest the which ensures that, for example, as we are discussing the last class, the holes are such that it can only allow the forward charge, it cannot allow the flame to enter it, and once the flame tries to enter it, it cannot sustain by itself, because the bore diameters or sizes are not favorable for it. So, that way the flame is killed at this stage itself. So, at any kind of things for explosion needs to be avoided, we require the flashbacks not to happen. This is exactly over the years our cooking gas cylinders are designed. Although there are accidents are happening, but not due to its design, but due to something else, negligence. But designs are such that either at any circumstances, by mistake, if charge is on, if your regulator is not functioning properly, if it is regulator is functioning properly, at no circumstances the flame can propagate back to the cylinder. But if those defects are there, then normally the accidents happens. So, if at all, and some cases explosions are required, some cases explosions are not desirable. So, explosions, something like when you think about controlled explosion, it can give a short duration thrust into the system. So, these are some critical features that we looked into while talking about laminar flame. Then I will try to move the factors that controls the laminar velocity. Two major factors are there, temperature and pressure, because these two parameters essentially rises. First thing is that the flame speed is strong dependence on temperature, and also because that is mainly for hydrocarbons, and their activation energy falls in this range 1.67 into 10 to the power 8 joule per kilomole, and this increase in the temperatures leads to dissociation. And one simple thing we can correlate mathematically, or correlations that can be developed, is that in the domain of 300 to 600 Kelvin, the increase in the flame speed, the increase in the temperature from 300 to 600 results in the flame speed increase by a factor of 4.3. So, flame speed increases with temperature. So, the dependence of flame speed with temperature is correlated by this expression. Dependence of flame speed with respect to pressure is correlated by this expression. Where we talk about this flame thickness, which we talk about 1 mm or less, is delta is equal to twice alpha by SL, and alpha is nothing but your heat transfer parameter, thermal diffusivity K by rho Cp. Other part that the flame speed depends is the equivalence ratio and flame type. Equivalence ratio creates a major role because depending, when you say that if you refer one typical diagram which we have discussed earlier, the role of equivalence ratio in the form of heat release or adiabatic flame temperature, we see that at equivalence ratio of close to 1, or at this case at least 1.05, heat release is maximum. This is normally what you see, and for all hydrocarbon fuels this number is fixed. That is what we say adiabatic flame temperature when it approaches. It is true for all kinds of hydrocarbon flames, but these numbers will be different if you are using hydrogen. Why it is say? Because hydrogen's flame speed is much faster than any kind of hydrocarbon flame, and here it is the case of propane. So, it is a propane air mixture. Why it is so? Because if you if you see here, this alpha plays a critical role. Thermal diffusivity and mass diffusivity of hydrogen is many times higher than the hydrocarbon fuel. So, when we have this, when you have hydrogen into the system, since the flame speed is higher, the reaction kinetics is much faster. So, that is the reason we say that in the presence of hydrogen, reaction kinetics is faster, and this also helps that non-formation, because when you have a rapid reaction, the relative slower reaction which is absent when there is a presence of hydrogen, and in fact it also acts as a kind of a catalyst for a favorable case situation. Another relation and it is more versatile, but here if you look at here these cases, this flame speed, because when this concept was evolved, people tried to see dependence only on pressure or dependence only on temperature through this correlation, but simultaneous control of pressure and temperature is not there. So, that way another generic formula was formed for developing a laminar flame speed, and it is based on the correlations which are developed with reference to a reference conditions and with the conditions at which we are looking at, or any arbitrary conditions. The arbitrary condition is nothing but temperature of unbound charge and pressure at that point. But when you look at this flame speed at some reference pressure and temperatures, so this way we can calibrate a systems with certain pressure and temperature as a reference conditions, and it will give you a corresponding laminar velocity or burning speed at that reference conditions. So, this is framed in this manner, ratio of temperatures, pressures. Additionally, it also looks after any kind of diluent present in the phase charge. So, that means if the mixture is not perfect in the form of fuel and air, if there is some additional components present, and if you are able to quantify that mass fraction, then this can be also linked to laminar split calculations, and this particular relations always valids when temperature is higher than 350 Kelvin. And this reference condition is calculated by some parameters. These parameters are specific to fuel air charge. This can be we can get from data book, and phi and all these are the terms that constants phi, B1, B2, they depend on that. So, all the numbers are known. So, basically what you know, you all know the reference conditions, and if you are able to know what temperature or pressure you need to find out, then we can find out this value. In some cases, if this Y mass fraction of any other undesirable products is absent, so this factor stops with this calculation stops at this point. So, this becomes 1, this term becomes 0, and it has no effect on the laminar speed calculations. This is most standard relations that are being followed as long as your temperature is higher than 350 Kelvin. So, I have explained all these things. Now, with this we say that there are some laminar speed calculation is there, we will be able to get, and once the flame moves, at least through this correlation we can find what is the velocity. Now, I am just trying to give some repetitive things which you will find from classical textbooks of any IC engines, just to correlate that what happens because those point of time we normally do not talk about the details of flame, but once we have flame generated in the engine, and we say there is a rise in the pressure as well as temperature. Now, if the rise in pressure and temperature are not desired as per this user, what is the going to be end effect? So, this is the question we are going to normally study for homogeneous air fuel mixture, and if the combustion is not complete, what is going to happen? So, one thing here is that the role of flame is to kill all the phase charge, because it has a characteristics of rise in the pressure. That rise in the pressure we subsequently ignites the next layer of phase charge. So, in the IC engine, initially we have a, if you can see, this is your engine domain. This is just to give a schematic. You have engine domain, spark initiates a flame, and that engine domain is designed into 4 zones, and it can be n number of zones. Just to explain how the flame moves at when it is at one instant of time. So, initially zone 1, zone 2 or zone 3 are of same pressure and temperatures. Once you create a spark, in the zone 1 the pressure temperature rise shoots up, because the flame generates and it tries to propagate. At one instant of time, zone 1 is now full of combustion products, but zone 2, 3, 4 are still unburned charge. So, as the flame moves, it tries to spreads the rise in the pressure and temperatures. Slowly it is moving in their directions. So, this one we, in the ice engine term, we call this as a flame front, which propagates into the in the cylinder, and this propagates with a flame velocity. This is nothing but which are our SL, and this flame propagation is caused by heat transfer and diffusion burning of the fuel molecules from the adjacent layer of burnt mixture. Where is this? Where it gets the charge? For example, it burns this layer, it gets the momentum from this, from this previous charge. Now it went to this another kind. This momentum is further raised. So that way, that way it gets energy in the form of heat by adjacent layer of unburnt gas mixture. This keeps and this for a homogeneous mixture, we typically have that flame velocity is of the order of 0.4 meter per second. This is just to quantify some kind of number, and this is observed in this equivalence ratio of this 1.1 to 1.2. Now, if the equivalence ratio is not favorable, means from the next layer of charge, if the flame does not receive sufficient energy, it assumes that it is gets cooled. Subsequently, when it moves, your heat is continuously rising. If it is not rising, means the flame is getting cooled, because unburnt, because the flame doesn't have sufficient, the charge doesn't have sufficient strength. So that way equivalence ratio has to be maintained in a with a rich value. Now three kind of broad regions that we get in this combustion process: ignition, flame development, and flame ignition and flame development, flame propagation, and flame termination. Why such things are required here? That if you look at this figure again, the flame front propagates. Its main role is it has to kill all the phase charges, and while killing all the phase charges, it should not kill at any intermediate locations. It should kill all the charges when it starts its journey from its spark plug location till the end. So all the charges has to be killed, or phase charges has to be consumed only when the flame reaches at the location 4. That is the most ideal situation. And through this process, it is viewed that initially you start with ignition, then flame development, flame propagations with certain speed, and the flame termination. Flame terminates at this. So that way we say at one instant when the flame is not there, it is only a fresh charge, and when the flame completes its role, it is the full of combustion products that has to come back. This is the most ideal situation. Now if it doesn't happen, then it gives some kind of undesirable phenomena, and in a qualitative way we call as a knock, which quantitatively way it is a undesirable pressure pulses, which means that pressure rise has happened, still the flame is there. Pressure rise has happened, but still the flame is sitting in the chamber. So those things we see in the pressure traces or temperature traces when you actually take it. So this is the most classical diagram that you see in the form of P theta diagram, pressure and crank angle, where we start our ignition. Maximum pressure is somewhere seen when phi is equal to 1.05. Sorry, this is phi is equal to 1.05, At that point we ensure that we have adiabatic flame temperature, pressure is sufficient here, and ignition, this is the flame propagation zone, and finally at this point when when we are towards the end location, the flame started terminating. And typically during ignition phase and development, it is done through a spark plug. With that spark plug has some it's nothing but a electrode, and it just a point to be noted here that we create a voltage potential about 25 to 40 kilovolt that turns out to be maximum current to be 200 ampere, but it is not that significant because it lasts for 10 to the power minus second. And during this time the temperature shoots up to a very large value, because during the lasting period of the combustions. But however, you really do not have to bother so much temperature, because whatever the situation that happens in a nanoseconds level. This is a typical curve that we get in terms of voltage and current when you do in the spark plug, but what we require through the spark plug is very small quantity of energy in the range of 0.2 megajoules. Now these are the some standard things that when during a flame propagation period, the fuel air mixture is consumed about 80 to 90%. So initially that's a very small amount. During flame propagation period, the fuel air mixture is consumed about 80 to 90%. So this part I have already explained. As the flame plant moves in the combustion chamber, what it causes. Either it can cause knocking, or if it doesn't reach at this point. This particular experiment shows that when suppose your flame front is at some location, and it has not reached this because undesirable mapping of pressure, temperature and charge. So knock can happen only at this location. Knocking cannot happen because these are already the combustion products have already formed. So during this is another curve that shows that what is the mass of the charge that gets burnt with respect to percentage of volume which is burnt. Here also the same things which I have explained, they are written in this manner. What we look at is this particular figure, what happens during a knock. So if during the flame propagation period knock can happen, so how? Because for a normal combustions the pressure time trend is smooth. Now when there is a slight knock, because the highest pressure is felt at this location where equivalence ratio is close to 1. At that point of time, if we see pressure pulses in erratic manner, that is a tendency of knock or higher pressure pulses, and with heavy knock these oscillations becomes more significant. Now at which location it can happen? It can happen towards the end, because the flame has not terminated, the pressure has increased, so it tries to give some pressure onto this wall of this cylinder, that is trend is reflected in the form of pressure traces. These are some of the things that which is classical stuffs, which is the concept of flame propagation zone. There is another term called as burn angle, which is the parameter that quantifies that the during certain time the charge gets consumed. That is the period we call this as a burn angle. Then final case that the flame has to be terminated. This has to be terminated when the flame reaches here, and during this phase last 5% of the fuel air charge gets consumed. So these are the some of the thing. There are some situations we can see there is a self ignition. In fact, the self ignition is one of the characteristics why that is a pressure rise, because the flame has not reached, but the charge which happens to be here and which happens to be burned by the flame, what it does, it self ignites on its own. Because of this reason, these pressure pulses shoots up, and these pressure pulses are detected through a phenomena called as knock. Okay, so this is all about this lecture that talks about the concept of laminar flame. How that laminar flame concept we are doing in the case of we are viewing in a homogeneous mixture of burning of fuel and air in an IC engine, spark ignition engines. So this slides also talks about some introduces some kind of solving problems for laminar flame, and first problem is something like correlates between the onboard charge and flame velocity, that through that relations one can have to find out for a particular case methane air flame what should be the flame velocity. And this talks about the horizontal and vertical distance through this because if you view this flame in a plane, we have horizontal distance and vertical distance, we have angle. So during that phase, what are the how the flame speeds is evaluated. The another problem that talks about the that will give you about the importance of this particular correlation, general correlations to calculate the flame speed from its at any arbitrary given situation with respect to a reference conditions. So this is all about this lecture. I will conclude here, and the next lecture will be given by Professor Markus. Thank you for your attention. Take break.
So break until 11:50.
Yeah.
Short break. Yes, okay. It's possible. Thank you. So, welcome back. Shall we start? Video ready? Seems so. So, we have in the lecture plan we have 4 hours for laser diagnostics, but I want not so to dive too deep in physical chemistry to discuss with you the details of spectroscopy. So the focus of the first part here is on what reactors can we use to examine combustion chemistry. Some I have presented you already, I think 2 days ago. Today we will have a look at rapid compression machine and shock tube in detail. So the combustion chamber we have discussed already. So with these reactors we can examine the reaction mechanisms in detail, especially selected elementary reactions. We can use other reactors we have already discussed too. So finally we get the information we need to describe the combustion process in detail, for example in a combustion engine. So what do we need here to predictive modeling? And the question is, okay, hydrocarbons, we know a lot, but what is with future fuels, future advanced for future advanced engines? So first of all, we need, of course, a detailed understanding here of the elementary reactions and mechanism. So we have to examine the elementary reaction steps. Then we have to develop proper sub-mechanisms. Finally, comprehensive and detailed kinetic models. So therefore, we have to apply a lot of work. We can examine unimolecular decomposition recombination at high temperatures using shock tubes. We can use high pressure flow reactors. We can perform optical measurements. We can use the advanced optical light source for mass spectrometry. And all together we can combine the data we yield to develop the mechanism finally. The optimum setup would be a homogeneous 0D reactor where temperature and pressure are in the relevant range. It would be perfect if we have initial conditions 700K 1 bar, and with 1 click we would yield the interesting high temperature, high pressure region within the shortest possible time, and then our examination could start. So between the initial condition and the condition we are interested in, there's of course always a gap, time gap we have to consider. the reactor should be perfect in a way that we have a homogeneous condition, though, so there's no disturbance by vortices, by cooling effect or whatever. And it would be nice to measure all reaction steps we are interested in. Of course, this does not exist, so we have to use different systems for different characteristic variables. So we have discussed already combustion cells, flames, flow reactors. I will say a little bit about steered reactors here today, and will focus on shock tubes and rapid compression machines. Nice. So the advantage of these two measurement devices, so shock tube and rapid compression machine, are we can examine ignition delay time at given conditions, and we can perform concentration measurements of individual reactants. So we can really also look on very specific reactions, selected individual elementary reactions. So we have discussed yesterday in the Cantera part ignition delay time calculations, which we compare to also experimental data, and there I've shown you that they used a bath gas of 90% argon. So the idea here is to use bath gases, so to dilute your mixture as much as possible, so that you can really focus on specific conditions. Okay, concerning the others, I would just want to briefly introduce this jet steered reactor. So this was not discussed until now. The idea is to have here a perfect continuously steered reactor. So yeah, we have seen this yesterday in Cantera. So you have a homogeneous reactor with specific inlet and outlet conditions. Especially the inlet conditions you have to know in detail, and you have to know the temperature of the reactor and the pressure, and then you can use these experiments, for example, to examine your chemistry. So the idea is we have a reactant plus carrier gas, which is going through this pipe into our steered reactor. Here we have a preheating zone, but the interesting temperature is in this area here. So we have cold mixture here without any reactions hopefully taking place, and then this is heated up as fast as possible, and then it reaches our reactor, and after a given residence time it leaves the reactor again, and then we can analyze the gas flowing out of the reactor. Depending on the residence time, temperature, mixture composition, we can learn a lot about the chemistry here. So, of course, it's crucial to have a homogeneous mixture. Therefore, there's a specific setup, mostly used in literature, with 4 inlet nozzles. So 2 outflows are in this plane. One is going up, one is going down. So the idea is to create a flow field which gives you a really perfect homogeneous mixture. And this is possible in a given range, of course. So this is quite a nice setup. However, what we have to consider, this is normally not optical accessible because it's inside an oven to heat it up to a specific temperature. So we can only examine the gas composition at the outlet. But this is sufficient for a lot of experiments, and this setup can be simulated with the continuously steered reactor model I've shown you yesterday. That means simple 0D simulations can be performed to examine the chemistry in detail. So here I'll show you this in detail. Here we have this jet steered reactor, and here we have attached an set up time of flight mass spectroscopy. So we suck out some specific amount of gas out of the reactor and then separate the molecules concerning their weight. So we learned a lot about on the mixture composition. Here you see the mole fractions for different reactor temperatures, and these are important information. You see we also have, so the symbols are experiments and the lines are numerical calculations. So you can perform your measurements and then use these data to optimize your reaction mechanism. This is also for liquid hydrocarbons. Of course, you need a controlled evaporator and mixer here, but nevertheless, this could be done. And here in this example, they used a gas chromatograph to analyze the mixture composition of the outflow. So now I will come to the focus of today's lecture, shock tube part 1 and RCM part 2. So I've seen the shock tubes here in Guwahati already. Maybe these are a little bit longer, but the principles are more or less the same. And of course you have a different application here. So you have other topics in focus. Here the focus is of course on combustion chemistry. And here we see an RCM, so I will explain this also later in detail. So a shock tube is a high temperature combustion reactor for our application. Not for your application here in Guwahati, but for our application. So we have an instantaneous change in pressure. And this generates a shock wave, which we can compare to a frictionless piston. So we have a shock wave moving through our system, and this compresses our gas adiabatically. So we have hopefully a stepwise change in temperature and pressure at a given position. The advantages is quite simple to employ conservation equations here to describe the status before, this we know, and after the shock, which we are interested in, and with very high accuracy. The change in state depends mainly on the Mach number we want to yield and the isentropic exponent. We can adjust our setup concerning the temperature and pressure range we are interested in for our ignition or reaction experiment. So, and again, this can be seen as a perfect homogeneous reactor. So again, a simple 0D calculation is sufficient to examine the reactions, the chemistry we see also with an numerical model. So we don't have to consider about the geometry of the tube, any 2D, 3D effects. Ideal, if we look at on an ideal way, so in 0D reactor is sufficient. Of course, only for a short time. And the real advantage is there is no pre-induction chemistry. So it's more or less an instantaneous change from cold mixture to hot mixture. And after this change, the chemistry will start. That's the advantage here. If we use, for example, this jet state reactor you have seen, we have a preheating zone. And of course, when we start with 300 K and have 800 K in the reactor, there is a slow change in temperature from 300 to 800. And at that time, already chemistry can take place, which may disturb our experiment. So here we talk about 700 K, which is, I think, really difficult. Especially at 700 K, chemistry is quite slow. So it's a problem here with this short experimental time we have. But we also can reach thousands of Kelvin, several thousands of Kelvin. So it's perfect for intermediate and high temperatures, and it can be used with some limitations also for lower temperatures. So the idea is here we have a driver section with high pressure, and we have a driven section where we also can use lower pressures, lower pressure than ambient pressure. And we have a diaphragm which is separating these two sections and can be opened in a controlled way. And after this diaphragm has opened, the high pressure gas expands into the lower pressure region. So from driver section into driven section. So we have an increase in pressure, so the pressure wave moves, the shock wave moves to this tube, hits the end ball, is reflected and moves back again. So we have one rise in temperature in this volume at a given time, and after the reflection we have a second rise in pressure and temperature. So this pressure and temperature here, which we reach after the reflection of the shock wave, can be adjusted very precisely using proper pressure ratio, using proper driver gas and so on. So we can really adjust precisely the interesting parameters here. And after this initiation, very fast, nearly instantaneous initiation of our interesting conditions. For example, here we see our ignition delay time, or we see change of other concentrations, as we have the possibility to examine also optically the conditions at the test section. So what is happening here? So when we open the diaphragm, we have a shock wave which moves through our shock tube, hits the end ball, and is then reflected. We also have, of course, an expansion fan going in the other direction, which also hits then the other end ball and is reflected and moves through our shock tube. And of course we have this contact surface, so the area where the high pressure gas and the low pressure gas come together after opening of the diaphragma. And of course here we have mixing and so on, a lot of disturbing processes. So and this contact phase moves behind the shock wave through our tube. So at that time our experiment can start. We have reached our interesting conditions. And we have an observation time which then depends on the arrival time of either the contact surface or the expansion fan. So one of them reaches this area earlier, depending on the tube we are using. And then, of course, our volume will be interfered by other processes, so we no longer can observe our interesting reactions here. But we have some milliseconds and so on, so for most processes, especially at high temperature, of course, this is very sufficient. So we need to know the thermodynamical data of our gases we use, but these are well tabulated, so heat capacity for constant pressure, constant volume, inner energy, enthalpy, isotropic exponent, sound velocity, Mach number, this we can find in literature. This is well known for the most gases. So how can we use this information to calculate the interesting reaction conditions? So what is the pressure and temperature after the reflected shock wave has hit our observation volume? This we are interested in because at that time the reaction starts, and then we can for example measure ignition delay time and so on. So we have at the beginning a quiescent gas mixture, and then our shock wave moves towards this quiescent gas mixture with the specific velocity. And this we can describe with a moving coordination system. So we are moving towards the shock wave. So and the initial velocity here is equal to the velocity of the shock wave. So and we are interested in, okay, this is our initial condition with known temperature, pressure, and this moves towards our shock wave, and then of course temperature and pressure will change, density will change, and so on. And of course the velocity, this is not so much of interest. So when we look at this configurations, is it possible to determine the pressure, the density, the temperature, the velocity behind the shock wave? So we set up the general conservation equations, we cancel all negligible terms, and then we transform the equation and hopefully can calculate the conditions behind the shock wave depending on the conditions before the shock wave plus the velocity of the shock wave. So when we look at the fundamental conservation equations, this looks quite different. So we consider here only two dimensions for mass conservation, momentum conservation, and energy equation. So we have of course a change in time, and we have change in two dimensions, so it looks quite difficult. But when we want to simplify it, we can use several assumptions which are valid for a broad region here. So first of all, we don't have any changes perpendicular to the flow, so in this dimension. and no velocity in this direction. So these parameters we can set to 0, and we assume we don't have any change with time, which is valid for a given period too. So we can, this derivative can also set to 0. So we assume it's adiabatic and we don't have any friction. So we don't have shear stresses and we don't have heat flux. So these parameters can also set to 0. So we are lucky most of the variables or terms we have are deleted when we apply these assumptions on our equation system. So this is what is left over. So the momentum is conserved, and with this we can calculate velocity and pressure and energy in the second behind the shock wave. When we integrate this, okay, we see this is the outcome. Density, velocity before and after the shock, and here enthalpy and pressure before and after the shock, and with the ideal gas relation we then can calculate the temperature. So we have density, velocity, pressure and temperature. So these are the 4 quantities we are interested in. So quite simple, quite perfect. So with this we can set up our equations here, and here we also already have included the isotopic exponent and the Mach number of the Mach number of the shock and the isotopic exponent and of the driver gas. So you can see with these we see that the ratios we are interested in depends only on the composition of the mainly of the driver gas and on the initial temperature, pressure, and therefore also initial density. So, and if we increase, for example, the Mach number of our shock, we can increase the density, the pressure and the temperature behind the shock. So here you can see the influence of this isotopic exponent. So helium 1.67, 1.4 is air, and 1.2 I'm not sure is maybe carbon dioxide. So you see, the higher the isotopic exponent, the lower is the pressure ratio. However, we are more interested in the temperature change. So here we see, if we use this helium as a driver gas, we have can reach higher temperatures at the end. So what is happening here in detail? So this is what we have before the shock, and you see here already numbers, so 4 and 1. So if you look at literature, you will often find, for example, the ratio T5 over T1. So the numbers you can find in literature I have given here. And I will explain it at which time we are looking at interesting conditions. So this is called section 4, section 1. So then the diaphragm is opened, we have our expanding shock wave, we have our shock wave, our expanding fan, we have our shock wave here, and we have our contact surface. So we then yield two more regions. You can see here. So, but further all I want to describe here temperature and pressure. So when we open the diaphragm, the pressure moves through our tube, and where the shock wave was, the pressure is increased, and then we have this position of the shock of the contact surface, and you can see it here in the temperature region. We may have an increased pressure, but here we have also a mixture of the driver gas and the driven gas, so the temperature is already quite low because it's disturbed by the mixing process and so on. And however, in the region between the position of the shock wave and the position of the contact surface, we have more or less homogeneous high temperature region. We also have this section 3 here, so between the expansion fan and the contact surface position, where we have higher pressures but lower temperatures. And we still have here 1 and 4, as we have still high pressure region and low pressure region here. Then at the end, this is what we are mainly interested in. So when we hit the end wall here, the region 4 is gone. But more of interest is we have the hit of the end wall here with our shock wave, and the reflecting wave is going back. So we have a further increase of pressure in a specific region, leading to a further increase of temperature. And this is what we are interested in normally, and this is the so-called section 5, and as I've said, this is what you normally find in literature, the ratio T5 over T1. This is why this is given as T5 over T1. So when here we have another plot for this, so we have very short time for T4, T1, and we have some time where we have section 3, section 2, but of course normally we are interested in section 5. And the observation time we have depends of course of either the contact surface, which is here, the faster one reaches our observation volume, or this expansion fan reaches our observation volume. This depends on the tube parameters we have. But until one of them reaches this area, we have some milliseconds to observe, hopefully some milliseconds to observe the interesting conditions. So in the ideal case, when everything works properly, it's frictionless, we have ideal gas behavior, so we can use this incident shock to calculate the conditions using the conservation laws and the equations of state, which we have discussed already. Another important quantity is then the Mach number of the shock, which depends on the velocity and the velocity of the shock and the temperature, gas constant, and isotropic exponent. So At the end, when we have this reflected shock, we can use our set of conservations again. And finally, P5 to P1 or T5 to T1, the interesting parameters, are a function of the Mach number and the isotropic exponent of the driven gas. I think I have often said driver gas. Of course, this is not correct, of the driven gas. So gamma 1 and the Mach number of the shock. So we have broken down the complex problem on two quantities, which is often helpful. So the experimental conditions behind the reflected shock wave depend on the initial state. So initial fill conditions and the shock strengths. The shock strength depends on the Mach number and the isotropic exponent, and of course the isotropic exponent of the driven gas depends on the investigated fuel mixture. So the Mach number here depends on the ratio of the conditions in section 4 to the sections in the driven gas. So sector 4 is the high pressure region. So the advantages here, it's quite simple to generate the interesting conditions in a broad pressure range and temperature range. We can assume that we have an homogeneous mixture with homogeneous pressure and temperature conditions instantaneously, and we can use this for several microseconds to examine the interesting quantities, avoiding pre-reaction chemistry. Of course, it has some disadvantages. We only have a few milliseconds. This is mainly the limitation to the lower temperature range. We have one experiment, so where we may perform also some laser-induced fluorescence or whatever, but we have only one shot per experiment. Then we have to refill the tube. We have to put in another diaphragm, so it takes some minutes, some time. So it's quite time consuming, and the number of the statistics you have are quite small. So of course some disadvantages. But we can use shock tube experiments to examine elementary reactions, and we can have it optical accessible, so all typical diagnostic methods can be used here. We can determine ignition delays based on different criteria, which, as we have discussed yesterday, is important. You should use the same criteria in your simulations compared to the experimental results. And we can also examine quite complex reaction system like a soot formation. We can determine formation of particles in the observation volume, for example. So how does it look like? So first of all, we can use here the pressure sensors. Even though some of you have worked here with temperature sensors. So the classical setup is using piezo pressure sensors, and then you can, for example, yield the velocity of the shock by different positions of your pressure sensors. And this is what you see here, for example, the pressure at the end ball in our section 5. We see the increase of pressure here already after the reflection wave, and then it takes some time until ignition takes place and the pressure increases further. So this can be used, for example, for a simple ignition delay time experiment. But if we have an optical window, we also can look for chemiluminescence. So CH and OH are typical radicals for hydrocarbons, hydrogen. So we can measure the emission in the range of 308 nanometers and or 430 nanometers, which are the typical bands of these two radicals of interest. And we see an increase, and this can be used, as we have discussed already yesterday, to determine an ignition delay time 2. And this normally not gives better ignition delay time, but it gives us a delay time which we can better compare to our numerical results. We can use other optical techniques. So we can have a laser light source here. When we have windows here, we can measure, for example, absorption based on Lambert-Beer law. So when we have a laser with a well-known wavelengths, and we know there's absorption from a specific molecule in those wavelengths, we can use this laser, measure the absorption, and then we can, as we know the distance here, we can calculate the concentration, the amount of interesting molecules in this area. So this is a function, the ratio of the light intensity is a function of mixture composition, but also of course pressure and temperature. We can use also Schlieren measurements. I have to check if this video is running here. So we look now in section 5, and hopefully see shock is coming from the left. Okay. Sorry, it has worked on my computer. So what we would have seen is shock coming in from the left, going back, and then after a given time, ignition takes place. We can use a gas chromatograph to suck out some gas and examine the mixture composition. We have, after ignition, for example, quite simple setup, and if we perform this at specific times after the ignition, of course we can get some additional information and some final simple experiment here. So we can also examine specific elementary reactions. We have, of course, no single shot experiment, so we get one signal per experiment. But we can use this to examine specific reactions, which gives us some limited information, but this can be used, for example, together with numerical work to examine reactions in detail. Here in this example they have used butyl hydroperoxide and methyl formate in a bath gas argon, and then we have this incoming and reflected shock heating up our system. So these two molecules are separated. So here we produce instantaneously OH, more or less. Here we produce CH3. So, and for example, here we can see the amount of OH. So after the shock, here we have the decomposition of this molecule. OH increases and then it decreases, and the decrease here depends on the reaction of the OH molecule with methyl formate or CH3. So we can examine this one elementary reaction here in detail, and when we know something about possible second reactions here, where we can use, for example, numerical simulations, we can see here the sensitivity of OH concerning specific reaction as a function of time, and what we then see is that this reaction CH3 plus OH giving CH2 plus water is the main interesting reaction. So OH is very sensitive, the consumption of OH is very sensitive concerning this equation here. So we cannot use this experiment only to get information about the ignition delay time, but also we get further details about specific reactions here. But okay, back to ignition delay time. This plot we have seen, or a similar plot we have seen yesterday. So the ignition delay time of N-heptane at specific conditions. Here ignition delay time as function of temperature at too high pressure conditions. And we see again our negative temperature coefficient we have discussed already yesterday. So each triangle represents one or set of experiments at specific temperature and pressure. And so this is what we have done yesterday. The simulations here show sufficient agreement. So a shock tube, of course, then can easily be used to determine ignition delay times in interesting temperature range. But that's the past. Actually, this setup is mainly used to examine modern renewable fuels. So alcohols are of interest, dimethylfurane and so on. So different fuels are of interest today, and the idea is actually we optimize our combustion engine based on the fuel we have. So we have diesel, we have gasoline with specific composition, and so the combustion engine is optimized here concerning this the quantities of our fuel. But if we can design our fuel, then we can optimize the combustion engine for perfect efficiency, and then design our fuel for the conditions we need with this combustion engine. That's the idea. So to change the optimization way. And so first of all, then we need to know more about the possible design fuels we have. Yeah? So we performed similar experiments which were done with the classical hydrocarbons. So here this dimethylfuran in the ignition delay time are examined at specific conditions. So we yield again ignition delay time and can compare this. And first of all, it's very important to realize, of course, different molecules gives us quite different ignition delay times at higher pressures and at lower pressures. So this information then can be used to examine the difference further, and this is what we see here, that there are regions where we always observe differences between the molecules. So, and then this data we need finally to optimize our design fuel, which may be a mixture of these or other components. So I suggest to make a break here, lunch break.
Yes.
And we will continue 3:30, right? Or 2 o'clock? 2 o'clock? 2 o'clock? 2:30?
2:30.
Okay. So, thank you.
So can you please elaborate more on that expansion pendulum?
Yeah,
Expansion
of course. Sorry, we have time for questions.
Okay.
Sorry. So your question is?
Can you please explain more on that expansion pendulum?
Which?
Yes, sir.
What do you mean with explain?
Actually, what is the physics behind that? I do not understand actually.
Pardon?
What is the why it is being formed there? That zone, expansion band zone, why it is forming there?
So that's energy conservation. Of course, you have a shock in this way, because there is a compression, sudden compression. We have an expansion in the other direction. So here is high pressure region, here is low pressure region. So the shock due to this high pressure meets low pressure, moves in the one direction, and of course it expands then in the other direction. So pressure is increasing here and decreasing here. But this is normally not of interest. So this is not an observation volume. Therefore, I'm not aware that if there is there any work where they examined the influence of the expansion fan on the section 4. Because finally what is of interest is at which time the expansion fan reached our section 5. This is the quantity we are normally interested in. So, as you may have heard, I'm not an expert here because I haven't bothered about it until now.
pressure maintained in the test section,
Un-
in the pressure maintained in the test section,
Mm-hmm.
section 5 I think. So is it, what is the range of pressure that can be maintained there? Like in the real engine combustion condition,
Mm-hmm.
the pressure is varying like up to 50 bar, 45 bar.
Yeah.
So here somewhere I have seen the pressure is like 1 bar to 100.
Yeah, that's the initial condition. So, and we can go below 1 bar, but we can. This mainly depend on the strength of your piston or the tube you use. So 100 bar is no problem here. Mm.
Okay, so by increasing the length, what you have just shown, so that is the existing soft tube in the fitting. So it is having a driven length of 11 meter. I think.
Yeah.
So by increasing length, how fold the timing is increased?
Yeah, if we increase the length, we increase the observation time.
Yes. So
Yeah.
it's how fold it is increasing? What is the maximum amount of time? So there is number.
I have no guess here.
Reaction
Mm.
time.
No.
There is time before the contact surface or the expansion can meet the soft tube, the reflected surface.
Yeah, so we will see it after the lunch break. We always have a real shock. And this, what I discussed now with you, was a perfect shock. Of course, we also have disturbances due to the shock,
Yeah.
which influences the delay, the time. So it wouldn't help to have an infinitive long shock tube here, and then to have an infinitive long observation time. This won't work. So there are some limitations, but you have quite impressive long shock tubes in combustion experiments. So they have some milliseconds here, but I don't know the upper limit here. Sorry.
So can it replace RCF?
Hmm?
Can it replace RCF?
Yeah, that was the fear of the RCM guys. So as I've shown, up down to 700 Kelvin, we may use it. I think we then have a region where both can be used. One big advantage of RCM is it's fast. Huh? So we have a high repetition rate. That's a big advantage. So we will see it later today. So both have their advantages and disadvantages, and it depends on your application too.
But here the amount of gas required is in some 200 something liters. So at a single go you have to consume a lot of gases, and helium is anyway very costly.
Yeah, okay. You mean the cost per experiment
Yes.
are higher for a shock tube?
Yeah.
Yeah. Hmm. This is also okay. Scientists normally don't look at money, but this is of course of interest too. Yeah.
Yeah, we try here with nitrogen and helium also, but maximum time we go with nitrogen.
Yeah, helium is unbelievable expensive in our days. Yeah.
And with this driver pressure of hardly 25 bar, we go for maximum of 25 bar. And with that we can achieve a shock above around strength of 2.5 to 3 Mach.
Mm-hmm.
So by this XT plot, so we calculate the timing is around 1.2 millisecond, around that one. So
Mhm.
this reaction time, that's why we have not tried that concept here by putting the reaction mixture at the test gas.
Because it's too short, or what?
No, means that putting this reaction, making the mixture composition perfectly, and again trying this one, so that part we have not tried it. That's
Yeah. So we have just talked now about the length of the pipe,
yes.
but also you have to consider the diameter,
Yeah.
because we always have a real shock, and the combustion shock tubes often are very, very big in diameter, so it's also expensive then.
Here we mostly go for achieving this planar shock waves. So that's why we have kept 7 meter of long, and that is sufficient for us. 2 meter of driver length and 5 meter of drivel length. So that is giving us planar shock wave. So we have not increased that one to more.
Yeah, then of course if you don't have further needs, you don't have to
Yeah, that's
invest here more. Yeah.
And when we are in the mixture, when we are mixing the reactant, test gas, so how the homogeneity is maintained? The mixture is not homogeneous when you are putting a mixture there.
no, before it is mixed and the mixture is placed at a test section here. Right.
So when you
Separate mixture tank.
Yes.
fill in your mixture, normally you wait some time, and then you have hopefully increased and homogeneous mixture. But that's, for example, the disadvantage when you use ammonia. Ammonia then stick to the surfaces. So, of course, there are some effects which have to be considered. So until now, we have talked only about the perfect world, not the real world.
Actually, in PTB, like when you are using ethanol and and butanol, generally, what way you are doing that? I am asking.
Yes, yes.
Generally, what way you are doing? We are pre-mixing it and putting it in the driver section, or it's as it is. We are just supplying the gas inside it.
Yeah, okay. And butanol is a liquid,
Yes.
so of course we have a mixing device in advance, and then we normally have already heated above the boiling point conditions before the shock.
So that means it is being preconditioned.
Yeah, the precondition must be adjusted here, of course.
Sir, which gas we use as a driver gas here?
Yeah, normally it's often it's helium, but as we have heard, it's also expensive. So you can use nitrogen, you can use carbon dioxide.
And sir, here for shock, sir, diaphragm is moving, or we just remove the diaphragm?
Pardon?
Sir, here for moving for shock, we have to remove the diaphragm, or diaphragm is moving?
You have to remove it.
We have to.
Yes.
Yeah, it's normally it breaks at a given pressure.
Okay, and both gases will mix together, no? Driver gas and driven gas both mix, no?
They mix.
Mix together for shock.
Yeah, that's this region here.
Yeah, both gases mix together.
No. So before the shock, we have a clear separation,
Okay.
and then this diaphragm is opening, and then of course we have a mixing region. But this is all not of interest normally. The only interesting factor is how long it takes the contact surface to reach our observation volume. So, if there are no further questions, enjoy your lunch, and we'll meet again at 2:30. Thank you.
phi 0 पे u 0 है तो c equal to 0 है क्योंकि psi 0 है तो c 0 है psi आएगा u का बट psi किसका नीचे है पाना है तो फिर y का क्या पता
तुमने ये इसको 0 0 लिया इसको किस पॉइंट पे 0 0 लिया इसका इस पॉइंट पे लिया
psi हमारा y का फंक्शन है
मैं क्या मैं कह रहा हूं कि मैं बताता हूं
Oh, thank you. So shall we start already?
You can start already, it is close to 3.
Okay, camera is running. So today in the morning we have discussed shock tube as a reactor, how we can use it, for example, to examine specific elementary reactions, or we can use it to determine ignition delay time, and I've shown you how simple it is to calculate the conditions in your volume after the shock. So the conditions at section 5, so temperature and pressure, can easily be calculated, and the equation system was quite easy to solve. However, in real life it's a little bit different. So we have so-called real shock tube processes. So in ideal world we don't have friction, for example. However, when you look here on the right side, there is of course friction, and there is a boundary layer at the tube wall, which may cause some problems. And this then, of course, lead to an effect that it slows down our shock, and so finally the shock wave is at a specific position at a different time, and what is more critical, the real pressure we will yield is lower than the pressure we would expect in an ideal case. So this is also shock delay and decrease of temperature pressure. So what we can do is, of course, we have discussed it in the morning. In combustion, typical shock tubes have a large diameter. This is due to the fact that we want to minimize the effect of cross-sectional constriction due to the boundary layer. We would like to have a low impact pressure and high filling pressure, as impact delay is proportional to the square root of Mach number over pressure. So heating of the pipe necessary for high T5 conditions. And finally, we have to optimize the opening of the diaphragma behavior. So, oops, sorry for the typo, shock boundary layer interaction. So it's not only the movement in one direction, of course, this reflected shock we have interacts also with the boundary layer. And so you can see here our reflected shock, or maybe you can see it here. So there is no longer a strict line perpendicular to our tube wall. Of course, here in the upper area you can see a bending here. So our reflected shock interacts with our boundary layer, and then of course we will have an area which is first of all not homogeneous, and we can even see it in the pressure region. So it influences of course also our pressure signal. So then you see, have it maybe seen here already on the Schlieren image. So we have a curvature on our shock, not the accepted straight line we see here. And we have heat losses to the wall, of course to the tube, but also to the end wall, which has to be considered. So now of course everything changes our T5 we want to get at the end. Then our gas is not an ideal gas. An ideal gas, we would see perfect impact, and we would have only transitory and rotational movement. But in real life we also have vibrational movement of the molecules, and this is an additional degree of freedom, which of course then led us to the effect that our heat capacity here is no longer constant. So then we have repulsion and attraction of the molecules. So like this classical Lennard-Jones potential, there is a reflection of the molecule when they come in contact to each other, or in repulsion. So this also of course has to be considered if we consider real gas conditions. So to summarize it, so for a caloric real gas, so we don't have a constant Cp value, and if we would consider thermal real gas, we have to include a real gas factor in our thermal equation of state. So we no longer have an ideal gas here. So on the influence you can see here for P5 over P1 or T5 over T1. So the yellow lines or symbols represent the ideal case. In pressure, the difference look maybe not so different, but you can see here in temperature, the higher the Mach number, the larger the deviation. And this of course means we don't know our T5 if we do not take into account these effects. Ideal case is constant conditions without flow behind the reflected shock wave, and states can be determined from the initial condition, as we have discussed it in the morning. But in reality, the choke retards due to the boundary layer growth, and we don't have a non-ideal membrane opening or diaphragma opening. So the states can no longer be calculated from the initial conditions, and stage change with time, even during our observation time. And pressure and impact velocity can be measured. So with pressure probes, we also have discussed in the morning, and temperature can be calculated taking into account real gas behavior and the measured impact velocity. So this means the simple equations we have discussed in the morning are not always valid. However, we can correct it if we use proper equipment, proper calculation methods. But I don't have any examples here. I would now switch to the rapid compression machine. This is mainly for low temperature auto-ignition and pollutant characterization, or auto-ignition and elementary reaction characterization. So there are of course different ones. So this one is, I think, similar to the one at PTB. So the typical temperature range is 550 K to 1100 K. So there's of course an overlap with the shock tube. And the pressure range is 10 to 100 bar end pressure. So after end of compression. So, and the idea is we have a pneumatic driving chamber, and we have a hydraulic braking chamber. I will show it in the next slide in detail. And finally, have our reactor chamber. So we use a piston to compress our gas in the reactor chamber to a specific condition we want to achieve. So here you can see a sketch of this. Now it's 180 degrees turned. So here's the reaction chamber now. And here we have the reservoir to drive our piston, which moves into this chamber here. And finally, we also have a braking system to guide the piston and to have a control piston movement and a controlled stopping of the piston. There are different possibilities you can have here, but the classical way is you just compress and the piston may go back. It's not stopped. Normally this does not influence, but there are also systems where they stop the piston, so it's blocked until the end of the experiment. So we have here a reactor, and for this example set up we have an inner core of 50 millimeters. Then we have of course ports for probing, pressure sensors, thermocouples and so on. We can have a movable end wall, and we have a variable stroke distance here between 150 and 250 millimeter. That means we have a variable and also a variable compression volume. So we have a lot of variety here to adjust the volume, and together with the pressure parameters we can adjust easily the initial conditions after the stroke. And what is important, so we can reach up to 100 bar before ignition. So maximum working pressure is 1000 bar in this case. So the brake system, okay, the main function here, we don't have to discuss all the details, but is to control the piston speed and the braking, so that you have a controlled and repeatable compression system for this purpose. The piston drive system, there are also different realizations you can find in literature. But here, okay, we have maximum working pressure of 50 bar and a pressure vessel of 100 liter. So after opening the valve, the pressure expands and moves the piston into our probe system. Oops, unfortunately this is in German. So we have here a guided piston. Which is the classical configuration, and here we have something, I call it a free piston, which is the normal, the modern realization. So first of all, we have to control the experiment, and we have to apply for a very short time our force to reach a short compression phase, so as short as possible, to avoid preheating or so. But of course, this has to be stopped at a given time, and it should be stopped in a way that there is no vibration or so. So that's also then requirement for the braking system. So again, it's not so easy as described until now. So of course we have heat conduction. So we have a much slower process concerning the compression phase compared to the shock tube. And we reach also lower temperatures. So we have a longer observation time. So if we have a fixed piston here, our volume does not change anymore. So everything has started and we can observe it, but however, after several milliseconds, some negative effects can be observed. So for example, heat conduction. So during the compression phase, there are heat losses, and of course after the compression. So one way to compensate it is also to have a large volume which you heat up with the compression, so that these heat conduction effects are as small as possible. That's one possibility. Then you have friction vortices conditions. So here in this region you always see something like a shear layer. So the piston is moving down, is compressing the air, and here at these edges there is a force flow which can be seen in experiments, which then of course has some influence. So here you can see an outcome of this. First of all, you don't have an homogeneous temperature field anymore, and you have induced vortices. So you have a flow field here which can be measured too, and this of course shows that we don't have an homogeneous mixture here, a quiescent homogeneous mixture at the end. Quiescent is not so important, but it should be homogeneous. You see here the temperature and so on. It's not an homogeneous volume. So, but there are also possibilities to get rid of these problems. Here they have some modification of the piston head, something where you have something like a suction section. So when the piston moves down, you won't see any vortices here anymore. So the the basic RCM operation system scheme, and therefore it's so easy to use. Is so you evacuate the system, you refill it with your fuel air mixture, then you pressurize a hydraulic chamber and open the ball valve of the pneumatic system, so you mobilize your piston, and the hydraulic piston is positioned in the grooves of the braking system, so you have a high pressure braking, and the hydraulic system then stops your piston, and you have hopefully an homogeneously air fuel mixture, which then may ignite after a given time due to the compression. Then you can perform your experiments with these compressed system. You can use, of course, classical pressure sensors. You can use optical windows if possible for advanced laser diagnostics. So all the things we have discussed already with the GIAN system are also possible here for this RCM system. So this is a classical pressure train race for a non-igniting inert case. So we compress here argon in this example with a given initial pressure and temperature. And this is maybe not visible. These are different experiments, and you see nearly no difference. So the compression itself works with high reproducibility. That's the first thing we learn here. Another topic is, you see already here an decrease in pressure, which is, if I'm correct for this experiment, also an effect, or mainly an effect due to cooling. So you can compare these results with ideal gas behavior, and then you can already get an information about how much heat loss you have, which then can, for example, be used for to adjust your numerical calculations. So for the numerical calculation, you no longer assume that you have one simple reactor, but you have something like an onion reactor. So you have different levels in your reactor, and the heat conduction or heat losses at the end wall influences the first layer of the onion. Then there is heat exchange with the second layer, and so, and finally you have your central core volume. So to optimize your numerical calculations here, you can get information about the heat losses from experiment like this. And then we have a classical setup here. We initiate everything, we compress. At the end of the compression, we wait until ignition takes place, and this is then the ignition delay time following this interpretation. So however, you can see it's not an instantaneous process. No, it's not like the shock wave where we assume an initial very fast compression and heat up of the system. There is a delay here, which also may have some influence. So, but again, you see here, I think 3 different experiments: ignition of butyl format here in oxygen and argon, very high reproducibility. So even though there are of course some disadvantages of this experimental setup, it works properly for a lot of applications. So we can measure pressure here, for example, and with this we can of course then calculate the temperature profile. I'm not sure if it's possible with Cantera, but they use here Chemkin, so it should be then of course possible. But as written here, there are also groups who are performing laser experiments to measure directly the temperature in the test vessel. What you also can see, we are talking about very long ignition delay times here. You remember for the shock tube we are talking about a few milliseconds. And here we also have an ignition delay time around 20 milliseconds. So of course normally we have lower temperatures, it will take longer, but that's the advantage of an RCM. We can go to these lower temperatures. And what can be seen, for example, here is a difference between single stage and two-stage ignition. So this is what we have discussed always until now. We compress, chemistry starts to react, and finally it decides, do we have ignition, yes or no. But of course we also can see here's something like a so-called two-stage ignition. So we compress and the chemistry increases, seems like it starts to ignite, the temperature increases further, and suddenly the reaction stops until after a much longer time. In this example, the ignition finally takes place. So, and the question of course is, why does this happen? So what is going on here? So this is again one example for this negative temperature coefficient we have discussed today. So first of all, we heat up, the reaction takes place and starts to ignite, further heating up our system, but we are in a range of the negative temperature coefficient, so the chemistry slows down with increase in temperature. So not everything is igniting, and then it takes some time before the reaction starts. So we have seen shock tube and RCM today, and we can separate them. So pressure before ignition in shock tubes, usually we stay quite below 100 bar, and we have a temperature range 800 or 700 to 2000 K. RCM, we have lower temperatures and pressures up to 100 bar. But what is more important is the measuring time. Here we talk to 1 millisecond up to 1 microsecond up to 10 milliseconds, and in RCM we have much longer observation times. We have to consider here the shock delay and the rear gas behavior, which I have shown you at the beginning of this session here. In case of an RCM, we have vortex formation, heat losses due to cooling, and also rear gas behavior. The advantage here is we can approximate it at an ideal compression, and we can approximate that there's no flow behind the reflected shock. And if this is not the case, we have tools to compensate for this, or to incorporate this here we have, first of all, low measuring time, but for me, much more important, we have a low testing complexity. So when we have a proper test stand, this can be automized. So we can prepare our mixture or program our mixture preparation properly. So this test can be run overnight without any additional support. So you can have ignition after ignition and do your probing, test sampling, whatever you want. And it's quite fast, so of course it depends on the cooling time of your reaction system. So you should not heat up slowly with subsequent explosions inside your RCM, this system. But if you know this and take care of this, you can perform a lot of experiments in a short time. If you look at the shock tube, you have a large volume, expensive, we have discussed it in the morning, and you always have to replace the diaphragm. So maybe when you are fast, we'll talk about 30 minutes per experiment, something like this. So instead of hundreds of experiments per day, so a typical student may make up to 20 experiments per day. So statistics is quite low here, and it's of course very complex to handle this. But here of course we have a very slow compression phase, and so of course pre-reactions may occur, which always have then to be discussed when you compare your experimental results with the numerical results. The advantages, we have an overlap. You have seen it when I explained the temperature range. And what is really impressive here, the open symbols, shock tube, the colored symbols, RCM. So very, very sufficient agreement between the two experiments. So if you have the possibility, it's always nice to have both systems in your lab, so you can again also double check your results of one of the apparatus with the other, which always is helpful. Double checking, as I said yesterday already, is always important. So again today there is no much need anymore for hydrocarbons, but for this modern renewable fuels like biofuels. And here ethanol as a simple alcohol, butylformate. Also here the in this example the overlap is quite good. And here we have RCM at lower temperature, shock tube at higher temperatures, and we see in simple Arrhenius behavior here for the ignition delay time of typical ethanol. So all the tools we have developed to examine classical fuels can also be used, of course, for modern newer fuels. What we also can do is, of course, a quantification. So we have here an example. RCM is coupled to two gas chromatographs. So we suck out some gas with the sampling system and examine then the mixture composition of the gas at a specific time. So here we have two columns, or you can even use more columns when you want. One for the smaller hydrocarbons, another one for the larger hydrocarbons. And this here, okay, we have a classical GC coupled with a flame ionization detector. So we have very, very precise measurement of the amount of the different hydrocarbons here. So we have several requirements here. We have to minimize the effect of the roll-up vortex, and we have to be sure that we have an adiabatic core. So we have a thermodynamically well-defined homogeneous mixture with a constant volume, constant mass chamber at the end of the compression. We have a fast compression and, okay, at our given typical temperature range. The piston has to be vibration-free during stopping. The charge temperature is often varied using heating systems up to 200 degrees Celsius before ignition, for example. Okay, we need optical accessibility, gas inlet pressure management devices, and so on, or sampling apparatus for species measurements. So what is the problem here? So we have seen this real behavior of the RCM. So we have complicated aerodynamic and heat loss effects, and that's the funny thing. So one RCM delivers really reproducible results, as I've shown to you for the non-igniting and also for the igniting case. So everything works fine, but there is not only one lab with an RCM on this world. There are different RCMs in different labs, and they show quite different results. So it's of course a hint that you have to examine the outcome of your results with your specific RCM carefully. Not like with the chalk tube T5, I can easily calculate, and P5, so I know everything. Here we have much more problems with this heat loss effects. Then this roll-up vortex I have shown you on a picture creates, as we have explained, so temperature inhomogeneity, which then of course influences the ignition delay time. There are different settings to handle the stopping of the piston. So as I've said, there are different realizations of RCMs in different labs, and one possibility is, for example, to really hard stop the piston so it's don't move anymore. And the other realization is this hydraulic brake system. So then it will move after a given time. Hopefully it doesn't influence your outcome. So if you both of these braking or stopping systems, of course, has some influence. So you always have a force acting here, which may include induced vibrations, and then you have to take care, for example, to have a proper pressure sensor. So some of the pressure sensors are very sensitive concerning vibrations. So the classical piezoelectrical pressure sensors measure a force concerning the force, they have to produce some electrons, some charge, And of course, if you take not care of this and have not the correct pressure sensor here, these vibrations also lead to an impact on this pressure sensor, creating additional charge. So this is then of course of importance, because you measure an additional force which influences your pressure signal and resulting then in not correct temperatures. So then of course, if we finally realize that we have deviations from our ideal adiabatic core, it's not easy to determine the temperature in the reaction chamber. And as I said, there are already simple numerical tools to take care of this. But nevertheless, this is always something you have to consider. You don't have a perfect system, at all conditions at least. And therefore you always have to take care. Are you still in the correct region or not? Or do you have to take additional measures to get or to handle this? So most of these problems can be handled if you take care of it. And I've said you can use even simple 0D calculations using so-called multi-zone models, like this onion model. You have different layers, so you have different multi-zone or different reactors interacting with each other. So you can take care of it if you measure, for example, the heat loss before you start your real ignition experiments. And okay, here maybe my colleague was a little bit optimistic. The perfect way was to have a numerical tool to use a complex 3D CFD calculation to examine the heat losses, the vortexes and so on with your setup. So that's it for the afternoon session. Do you have any question concerning RCM or real gas problems in shock tubes?
Yeah, I have read somewhere that the compressed temperature, so some people have calculated it by using the initial pressure and the initial temperature value. That compressed temperature,
Yeah.
so what they are doing is they are just putting the initial pressure plus initial temperature, and both of the terms are multiplied with the gamma value.
With the gamma?
Yeah, that means the index of Cp to Cp.
Yeah. So the isotopic exponent, yeah.
Yes. So by using this expression, so they are calculating the compressed temperature. So is it giving a fair value or it is just an approximation?
No, it's if you have an adiabatic core, it's correct. So you measure the pressure, and you know the initial conditions, so mixture composition or density, pressure, temperature. So then with this end pressure you can calculate the temperature in your adiabatic core. So this is the assumption we have a real gas behavior here, or an ideal gas behavior. But you always have to take care if it's correct or not. It's the first and simple way to do this. But I have shown you also examples where you can see it's no longer valid.
And one more question, as per the theory, as for rapid compression machine indicates, so it should go in a single go and it stop there before the reactor. So means while going for the compression process, how fast it should go and it should stop. So is there any specific dimensional constraint there, or
I can't give you any numbers. huh? Um, so, from the ideal point of view, the compression should be as fast as possible to avoid this reactions before you finally reach your end pressure before ignition. And on the other hand, this should be stopped immediately. So that you have a volume which is heated up in a specific way, and so the movement of this piston after the compression does not influence anything. But these are the two main problems. You cannot be infinitively fast with a compression, and you have a mass of several kilograms maybe, which you suddenly stop. So either you have a hydraulic brake system, so you try to compensate the vibration effects and so on with this not hard stopping using this hydraulic brake system, and so the force moving this back is also compensated. Or you have really a hard stopping system that you block the piston so that it cannot move back. But you always then have vibrations. You have an accelerated mass here which has to stop suddenly. So, and these are the two, for me, the two main problems, and therefore we have different realizations of RCM in the market. Each has its advantages, disadvantages.
how do those reactor chamber volumes affect?
What effect?
Reactor chamber volumes. So is it fixed for all the actions, or it is an attachment which is changed from time to time?
Yeah, so first of all, the larger the volume, the better. But of course, we then the question is how much does it cost? And this specific RCM has an end pressure of 1000 bar. So it's very, very solid. So you need a lot of steel for this. So the question is, of course, here we have, I think I have given the numbers here. So before, after to end of compression, that's not sufficient. So we have an inner core of 50 millimeters. So question is it sufficient or not? But if you increase it, it will cost a lot of more money. That's always the problem here.
Why did I ask this question? During my visit, it was in the breakdown condition, so it was open. So during my visit, so it was open.
Yeah.
So I inquired about that. So they told that this part might be replaced with some other attachment. So that is why I just asked.
So the piston part, or which part was open?
It was completely open, I think.
Yeah. They have often some new ideas. Yeah. Yeah.
How do you regulate the volume through this thing? Just by increasing the diameter?
No. This is so this outer part is not changed. But what you can adjust is the stroke. So how many millimeters, how much free volume you have here. So there is a small degree of freedom here. But nevertheless, so this is so not so important, because what we want to have is a homogeneous region here. Therefore we have only a small degree of freedom with the stroke, but this is more than the fine adjustment concerning the end temperature or pressure we reach.
Which is a better approach, soft tube or RCM? Which is a better approach, soft tube or RCM?
The correct answer is here, it depends.
Yeah, but it costs more, right? RCM costs more than soft tube.
Yeah, but we are talking about, okay, it's a lot of money, $250,000, maybe. So this is the number I know. I've seen at least some offers for this. And as I said, if you have an optimum test stand here, you can start the experiment and went to holiday for 4 weeks, come back, finish your PhD thesis, and everything is fine. So with a shock tube, every 30 minutes maybe, so you know it better than me, how often you can perform an experiment per day. So it has, the shock tube is of course better at higher temperatures, and the adiabatic core can be better described in my opinion. So more precise T5 and P5 compared to this compression, and you measure P, okay, but the calculated T then has maybe more error. But so I have shown it to you here. The overlap here for this specific example is, for me, it's astonishing. So, of course, I've said if you use different RCNs in different test labs, there are also deviations. So, what means now better? You always have to double check your results. But you are right. The big advantage of a shock tube is it's cheap. To buy it, but then to use it.
But in both the cases, the temperature calculation is from pressure, right?
Pardon?
Temperature calculation, T5.
Yeah.
That we evaluate with pressure jump or pressure calculation.
Yeah.
In both the cases.
So here you measure the pressure and then calculate the temperature.
In RCM as well as in the soft tube. Normally we do soft tube in the same way.
Yeah, but you can also, so you do it for a correction. Yeah, of course you do it. So for me, the disadvantage of a shock tube is also that you have a lot of that volume, which you do not use. So if you have a pipe of 11 meters with a diameter of 40 centimeter, but your interesting testing volume has maybe a length of 1 centimeter, you need a lot of helium.
So basically speaking, larger volume means you should prefer RCM.
No, I do not want to say you should prefer one of them. Both of them has their advantages and disadvantages. So the shock tube guys always prefer the shock tube, of course. Okay, further questions?
Yeah, does it give only ignition delay value or it can give anything?
Pardon?
Is it mean only for giving the ignition delay value or any other parameter installed here?
Please repeat again, sorry.
Yeah, using this we are mostly calculating ignition delay.
No, you also can examine elementary reactions like we have discussed today in the morning for this maybe I can show it to you. So it has the same flexibility here. Nah. So I've explained it. So you have one precursor to produce OH and one precursor to produce CH3. And these are in the best gas of mainly argon. So this you can do in the same way also within RCM. So you can also examine specific single elementary reactions.
Always you perform the reactor keeping argon into it.
Pardon?
In your test tube, when you put your sample, always argon has to be there.
No, but it depends on the reaction you want to examine. So I'm lost now. Of course, there is a specific reason why you use a monoatomic gas here, not nitrogen, which is much cheaper then. But
nitrogen has the implications that at high temperature they can react.
it can react, of course.
That's what
Yeah.
people talk about argon.
Yeah, that's the advantage here. Yeah. But I'm thinking of there is another advantage that you have a monoatomic gas. But okay, it's normally you dilute it, you use it as a dilutant. Yeah. And in case of RCM, it's not so expensive because you have a small volume. Okay, thank you.
So you can take your tea.
So do we have another presentation today?
Let's see, I don't know.
Introduction. So how this braking system is activated once the compression is done? Is there any kind of arrangement for that?
I'm sorry, I'm not the expert here concerning the mechanical details. So this, no, I don't know, sorry. You could ask your colleague, he has seen it open.
Yes, but he has option during operation.
So so I have to point out two things. This is work mainly from Ravi Fernandez group. So, and he has given me his slides to prepare this lecture here. So his group, they are the experts. And anyway, I'm a theoretical guy. I was never allowed to perform any experiments because otherwise I would have not survived. So I know something about how to deal combustion process numerically, but I'm not so the expert, especially not concerning combustion kinetics in the experimental field. So here you should join your colleague next time when he visits. He will visit Ravi.
You could have given today now. You could have presented today.
Sir, actually, at 4 p.m., the online participants will give them a patent.
Online participants, how many of them can you spare 1 hour there? Then? So when they are presenting, they should tell about yourself and start and take a one slot.
For online participant, and 10 minutes you will vanish. For example, some XYZ is there online. So he starts with his introduction and back topic. Take one slot. If that is the case, you could have dealt on us. We can give the. Just for introduction, how much time they spend? 5 minutes maximum.
So who has ever used Cantera?
Cantera.
No, not before? No?
We are not into that till now.
I'm really
Something with who you can, something is there, that can be demonstrated here.
no, so it's not running on my new computer. So as I said yesterday, the installation is really, for me at least, the problem. So I'm surprised because, okay, you are not working so much with combustion maybe. But after you have said, okay, here we have postdocs and PhD students, I would have expected that at least one or two of you have used this tool already. But of course, if there is no need, why should you do it? So, but it is for me, so it's the advantage is you can easily learn a lot. Of course, much more than listening to such boring lectures like here. You can play with the parameters, follow the tutorials, and get a feeling for this. And then when you then look at the fundamental lectures you have heard here, for example, today and yesterday and so on, then at least I then have realized what the professor wanted to say. During the lecture I was sitting there, so what? So much information in a very short time. But it's a very helpful tool. It's very cheap, it doesn't cost anything. And you have a really big community. So a lot of questions are written in different groups. So your generation is lucky here. So the internet has also some advantages.
Anything in your, you can sit, sir. Anything you talk about explosion?
Will come next week. Because explosion is also combustion process. But unfortunately an unwanted combustion process.
Well, lecture is over.
So next week we have 4 sessions with how to handle unwanted combustion processes, explosions. Okay, combustion. Handorf.